Let's see our first example with the moon orbiting the Earth. And let me just remind us of, let me get a different color, some of the things that we've defined. So let's see, we said that a center-seeking force, if I have a net center-seeking force, then I have something turning, mv squared over r. Where a center, so the center-seeking acceleration, that just means that it's turning, is defined in terms of its tangential velocity divided by the radius of the turn that it's making. There we go. And that this thing doesn't represent any one thing. It can be a whole host of things. This just says that I have to have a force pointing towards the center of the circle, and my center-seeking acceleration vector also points towards the center of the circle to make a turn. So in terms of this scenario that we have going on here, let's see, what do I have? I have two planets. Can I do a circle? Oh, that's kind of a circle. I swear the last one was better. Okay. So I have a net force then pointing down. Well, let's see, we know between these two things, what we've defined now is, or before that, was that the force of gravity always points towards the center of the Earth. So same here, no problem. That's just the exact same. So I have this force of gravity, and here's my moon, in case you weren't sure, and this is the Earth. Now what the question gives you is this radius of rotation. What that is defining for you is the center of the Earth to the center of the moon. That thing there, that is the radius of rotation. We're going center of mass to center of mass. And so I have this net force pointing that way, and I'll remind myself, because we're new to doing this, that my acceleration vector is also that way. And for the most part, at least for now, because if it weren't constant, we'd have to deal with the change in velocity. We're calling this tangential velocity constant. So it's going to be the same tangential velocity for this entire orbit that it's making for now. So don't worry about that. So let's see. Then I need to say, okay, I've defined this force. So the sum of my forces for the center is going to be the force of gravity, and that's it. There's no air resistance in space. So force of gravity equals the mass of the moon times the center-seeking acceleration, which is the mass of the moon times v squared over r. And for now, at least, we can stick with our standard definition that the force of gravity is the mass of the moon times the acceleration due to gravity. Although this is the thing we're kind of figuring out right now. So we're going to see that this is going to be defined slightly different. So equals the mass of the moon times v squared over r. And so lodi hodi, look, they cancel out, and we're very excited. So we're going to have gravity equals v squared over r. So this would be the gravity that it's experiencing out there, that thing that's kind of keeping it kind of perpetually falling towards the Earth, but going in straight line, or going in this circular motion. So now I get excited. I feel like we just have a couple variables to define, but then I look at this and I need to be very careful here, because that thing is in terms of kilometers, and this thing is in terms of days. And I reminded you in the first video that I did that the units on this unit can be a little bit of a pain, because we need to remind ourselves that we need meters, kilograms, and seconds. This one, the mass doesn't matter, but the meters and the seconds sure do. So I can rewrite this as my R equals 384,000. Let's see, what are there? There's 10 to the 3, or 1,000 meters equals 1 kilometer. So I can write that times 10 to the 3rd, that's replacing the kilometer, meters. Or I look at this and I'm like, that's hideous. So 3, 6, there's 3 zeros, 7, 8. So I can rewrite that as 3.84 times 10 to the 8th meters. That's my radius. So that part's done. That's not so bad. Now let's take a look at this days thing, because this needs to be in terms of seconds. So I can do this. I can go, let's see. So I have 27.3 days. And the name of the game with conversions is the thing I want to go away needs to go on the bottom, because that is it divided by itself, which makes 1. That's what we're looking for. So in one day, there are 24 hours. Need the hours to go away. So in 1 hour, there are 60 minutes times. In 1 minute, there are 60 seconds. So I feel like I'm there because I needed it in terms of seconds. I need it in terms of seconds. So let's check my units. Days cancel, hours cancel, minutes cancel, and indeed my period is in terms of seconds. Seconds is on the top. This is a period, not a frequency. So now I can put this thing into my calculator. Put this line straight across in the calculator. And I get what? I get a mess because it's not on the line, so I can't start typing right away. So 27.3 times 24 times 60 times 60, otherwise known as 3,600, and that gives me this ginormous number of 2.36 times 10 to the 6th. Whew! Yeah, that is a big number, but let's see. Now I can put this, rewrite this. We have our radius goes down on the bottom, this 10 to the 8th, and this is my period. Oh, why did I do that? Because I skipped this step, because the second time I've done this video. So I thought I did it in my head. Why did I do this? This is seconds, this is period. So this is T equals. Right now I have that in terms of V. So remember in the previous video I said, so we can define velocity in terms of 2 pi r f, or V equals 2 pi r over t. This thing has units of seconds. So let's see, this gives me, this is the distance around the circle per second. So per unit time that it takes. This has 1 over seconds as units, so it does the exact same thing for me. I have something here in terms of velocity. So I'm sorry, in terms of period. So my period is here. So I can rewrite this, that G, let's do a different color. G equals, let's see, this is going to be on the top. So I can go 2 squared pi squared r squared over period squared. Just took it from there. This is velocity. And that is over, or times 1 over r. So just saving myself some button pushing time. I look at this, this r cancels out, that squared goes away. So I can rewrite this as 4 pi squared r over period squared. So it equals 4 pi squared 1r. So this 3.84 times 10 to the 8th meters divided by, there's my period, 2.36 times 10 to the 6th squared. Now remember, if you're going to do this by hand with our exponents, we don't just add them together. This is an exponent that is squared, so they're multiplied. So this would be 10 to the 12th. So let's just go ahead and put that in our calculators. 4 times pi squared, don't forget it. That's like most ignored little piece of information. 3.84 times 10 to the 8th divided by 2.36 times 10 to the 6th squared. And I get an acceleration g. Yeah, no, we're good. So I get a g equals 0.0027 meters per second squared, and that got really messy. Sorry about that.